Okay, we're going to do a real quick review of naming compounds. Okay, first we have to determine what's in the formula so we know how to name the compound. Okay, chemists have systematic ways to do this. So if you learn the naming rules, you can name the compound's formula to determine its name, and you can also determine its formula from the name. Okay, so vice versa. By the way, things seem to have a common name as well, like NaCl would be table salt. Okay, or we might call it sodium chloride. So here's the rules. All right. So first, what we're going to talk about is binary ionic compounds. And the rule is you just have in binary compounds, you have a cation, one type of atom that's a cation, one type of atom that is the anion, and that's it. And you just name the cation, name the anion, but you got to put the anion version of that element. So it's an IDE ending. So the examples would be Na, sodium, chlorine, chloride. So you say sodium chloride. Doesn't matter that you have one of each. MgCl2, magnesium chloride. So the Cl2 doesn't matter how many because you only get the formula from the charges. So you already know what the formula is based off of what cation and anion you have that are bonded. Okay. BAI, that's barium iodide. Okay, so the trick is if the first one is a cation, you know that it's going to be an ionic compound. Okay, and cations always make ionic compounds. All right, so in the periodic table, you probably can determine the charge. Maybe you have one of those periodic tables that tell you what the charges are. So basically, something from the left side of the periodic table is going to be a cation. Transition elements we'll talk about in a second. So it might come from the middle. Anything with the middle is going to be cation. So cation. And then something from the right side will be an anion because we learned that they want to gain electrons. They want to be negative. So we're going to have one type of cation, one type of anion element. And in this corner, they're all negative, like in the yellow kind of spots. So to name this compound, CaO, that's calcium oxide. And I think that's all we're going to review for that. So the next type of situation that we're going to talk about is naming ionic compounds where there's transitioning metals. Okay, so the rule is if that first metal doesn't necessarily always have one certain charge. Okay, there's many metals on the periodic table that could have several different or a couple different charges. All right, so here's some common ones. Note the ones that are bright yellow. Those are ones that have more than one charge in there, and they could be, like, for example, iron could be +3 or +2. Cobalt could be +2 or +3. Nickel, same idea. These are generally the transition elements we showed you earlier on the periodic table. The exceptions are these metals right here are the other metals. Tin and lead actually also like to transition, both of them, coincidentally, between a +2 and a +4. Cation charge. We don't expect you to memorize that at all, actually. But it's going to change how we name the compound because we need to know whether the compound has tin-2 or tin-4 is how we're going to name it. And we're going to use Roman numerals. For example, copper with a +1 charge is going to be copper with Roman numeral 1, always in parentheses right next to the word copper. So that's the cation with a +1 charge. If it's copper +2, you need to make sure the name is copper-2, so the Roman numeral is 2 with little parentheses there. Notable exceptions, zinc and silver. Zinc is always +2. We never use Roman numeral on zinc because we don't need to. It's always +2. We never use a Roman numeral on silver because that cation is always +1. Occasionally you might see it, but it's not actually what chemists do. So here's your other exceptions, of course. Tin, Sn, +2 and +4. Those are other metals that also are going to transition along with the lead that could be +2 or +4. Okay, so now you know, if you got a cation that's a transitioning element, you're going to need to use a Roman numeral, but that's it. That's the only change. All right, so still, name of cation to name those with transitioning metal ions are still an ionic compound. Then you're going to say the charge of that cation that's transitioning in Roman numeral, and then you're going to say the anion with an IDE ending. Just you got to know your Roman numerals though. Usually, we're not going to go past 6 or 7. Occasionally, you could, but yeah. So make sure you have Roman numeral list handy for you if you don't have your Roman numerals memorized. All right. So, for example, cobalt, capital C, little o. That is not carbon and oxygen because the O is not capitalized. So the C and the O come together, and they're actually cobalt. The formula is CO2 with an S. So we have to name the cobalt sulfide with a Roman numeral by the cobalt because it's a transitioning. So how do you do that? First, determine the anion charge because anions are never transitioning elements. They're always the same thing. You can count on them. You can go to your chart of common ions, or you can look on your periodic table and you remember perhaps that sulfur has a -2 charge, always. Therefore, the cobalt needs to have an equal and opposite charge. These have to be balanced ions, remember? So cobalt has to have +2 because the sum of all charges must be 0 and it must sum the negative charges. Okay, so then what would be the charge on a single cobalt atom since we know the total has to be +2? Yeah, it's going to be a +1 because there's 2 of them. So then total, they'll make a +2. So we're going to call this cobalt 1 sulfide. So we have to use Roman numeral 1. And don't worry, in a compound with transitioning metal, they both or all of the atoms that are the transition metals are going to have the same charge. So you don't have to worry. They're going to be all cobalt 1 in the cobalt 1 sulfide. Okay. So iron chloride, you had to use Roman numeral on the iron to make it a proper name. So what's a total negative charge from the chlorine? Chlorine is always -1. If there's 3 of them, that's going to be a total of -3. So we know that the iron has to be equal and opposite and has to be a +3. All right. So it's going to be iron 3 chloride. Okay. So those ones were kind of easier. Let's try one that's just a little bit harder where it's not completely obvious. Okay. And I want to show you a trick. All right. So for starters, let's try iron oxide. Okay. Iron oxide, but we need to know if it's iron +2 or iron +3 because we don't know. So total the negative charges, and since every oxygen atom that's an ion has a -2 charge, all right, you have -2, and you're going to say there's 3 of them, so -2, -2, and -2. Total is -6, right? That's the total. The total charge on the iron, the positive portion of the atom, has to be +6. Yeah, so you need to know what the charge is on the individual iron atom. Well, there's 2 of them, so we got to take +6 and divide it by 2. So spread the charge evenly, and we're going to get, +3. So we know both of those iron atoms have a +3 charge because they have the total +6. All right, so it's going to be iron 3 because we need to know what the charge is on one iron atom. So you're going to call this iron 3 oxide. Okay, so I'm going to also teach you a trick. All right, so what works a lot of times, most of the time, for example, like copper 2. It could be copper 2, yeah, and bromine. All right, for starters, instead of just thinking about doubling the bromine or bromide, you could think about crossing the charges. We usually have the charge of the one atom become the subscript on the other. Right. There we go. And then since the bromine is -1, well, then it would just be 1 for copper. So yeah, that ends up working out. If you think of it in terms of positive and negative charges, yeah, we need to double the bromine. So we're going to basically multiply by 2. And the subscript here is going to be 2. So that's going to be your formula. We don't need to worry about putting a subscript of 1. Remember, chemists are lazy, and we just leave off the 1, and we would just write copper once. Okay, so don't worry about that. Put the 2 on the bromine, so that becomes, or the bromide, so it becomes copper 2 bromide, right? Because we had a +2 on the copper, right? All right, so it works to cross the charges. Some people say drop and swap, so you have to drop them and swap them. But it also works the other way. If you don't know the charge, say for example, you have iron or Fe2S3. Okay, this is some sort of iron sulfide, but we don't know if it's iron 2 sulfide or iron 3 sulfide. You could say, okay, I know the charge on the sulfur is a -2. There's 3 of them. Again, we're going to go with the -6 total charge, and we need a +6 total charge for the iron. We could divide that by 2, so it's going to be iron 3, or you could remember probably uncross the charges. So the 3 goes in the upper corner for the copper, and yeah, the -2 would work out in the upper corner by the sulfur because we know that the sulfur is always -2. So the 3 belongs to the iron. You could call this iron 3 sulfide, or you can figure it out the other way. So you decide what you want. This is iron 3 sulfide. Glad we fixed that. Okay, and that works for all compounds that have just a cation and anion. Okay, what about compounds that have polyatomic ions? Polyatomic ions, those are ions that have more than one element in the ion, but it's a group of ions that sticks together. Right, those elements always stick together. Could be a cation or an anion, but it's almost always an anion. Okay, here's a list. I don't make you memorize it in this class, but others you might have to. Most of these are non-metals. I think you've probably noticed. And the reason why they stick together, just FYI, is because they are covalent compounds, and they don't. They just stay together with stronger bonds. They just happen to have maybe an extra electron, so they're -1, or extra two electrons, so they're -2, or maybe even a -3, like these phosphates and phosphites. What you would do is just use that name. You would use phosphate for PO4 with a -3, if that's your anion, or phosphite if it's a PO3 with a -3, okay? And those always have the -3 charge. So you don't have to worry about transitioning polyatomic ions. They always have these charges on them. One exception with the anions being polyatomic is the one situation in ammonium. It's one of the few times, and for this class, the only time, that you're going to possibly have a polyatomic cation. Okay, so just be watchful of the NH4. It could come first. Remember, we always have cations first. And if that's the situation, then you need to use the word ammonium in your ionic compound. It's going to be an ionic compound if it has a positive first cation, right? Okay, so polyatomic ionic compounds, same idea, only you're going to name the cation, and then you're just going to name the anion. So it could be quite easy, actually, as long as you have the list in front of you, because you may not want to remember all of those polyatomic anions. And of course, the one exception of the ammonium. All right, so we get to this compound, KNO3. Use its cation for the first part. Yeah, we know that's potassium, the K+, that's potassium. And then NO3, if you can identify, the rest of it isn't just one element, it's a group of 2. It's a polyatomic, okay? Usually the cation is one element, and anion can be polyatomic. So use the NO3 name, which is nitrate, if you look it up. So this KNO3 simply becomes potassium nitrate. Notice the potassium is just an alkali metal. It is not a transitioning, so you don't need any Roman numeral, right? But in this case, iron is a transitioning element, and you do need to name the Roman numeral. I'm not even sure that I guess this exists. All right, notice this is polyatomic. It's not oxygen. It's OH. Look on your list. It's a hydroxide. Okay, so it's one of the few cases that a polyatomic ion actually has an IDE ending. It's right here on our little list. Yeah, you just use the word hydroxide with the iron, but you do need the Roman numeral on the iron. You looked up hydroxide. It's a -1. There's 2 of them. That's a -2 total charge, and there's only one iron. So we know the iron has to have a +2. Okay, equal and opposite totals. So we're going to call this iron 2 hydroxide. All right. This next one is, do you recognize NH4? It's the only time when your cation is going to be a non-metal or groups of non-metals, right? NH4, we know this is a +1. It's ammonium. And NO3 is the nitrate. So, just going to call it ammonium nitrate. There's no transitioning metals here. Okay, so what if we get the situation where there's no cation listed first? There's no metal listed first. These, and they're all non-metals. in this compound, and maybe hydrogen. In this case, there's no electron transfer. This is not an ionic bond of a cation and an anion. Electrons are shared. Here's an example, a common example of water. Oxygen likes to share its one electron that's unpaired here with a hydrogen. And then the hydrogen feels like he has two because he shares the oxygen's electron with himself. And oxygen feels like he has an extra electron. Oxygen also shares its other unpaired electron with another hydrogen. And they're both happy. Oxygen feels like he has 1, 2, 3, 4, 5, 6, 7, 8 in its outer shell. And this is what it kind of forms in its compound of water. Yeah, you guessed it. It's water. And the reason why these are interesting is because you could have carbon with its 4 electrons. It could form up to 4 bonds. We don't know. It's not determined by charge. And you could link carbon atoms almost infinitely. But we're not going to get into that. We're just going to say, hey, if the first atom is not a cation, if it's a non-metal, ignore hydrogen. If the first one is non-metal, then yeah, you're going to call it like covalent bonds. It's going to be a covalent compound. Okay, so for example, here's the rules. With no metals at all, electrons are shared. It's a covalent compound. By the way, they're all going to be right on the right side, non-metal portion of the periodic table. All right, including hydrogen. This is where you use those fancy Greek prefixes, okay? You probably want to memorize them. They're easier than having to look up a list. We have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And then I think we have dodeca for 11, duodeca for 12. Okay, don't memorize it if you can't. It's fine. Now, the only one exception is on the first element, if it's one single element in the formula, don't put mono on it. Okay, drop mono on the first element, all right? And then just like ionic compounds that are elements from the periodic table, they're going to have an IDE ending on the last element. So yeah, kind of cool. And if you have carbon in it, usually put carbon first. Okay, so those are the rules. Maybe you want to write that down. No metals at all. Flips it to a covalent naming. Use the Greek prefixes. Okay, for example, CH4. Remember, the carbon has to be listed first. There's no cations listed first, at least. And there's 4 hydrogen. Here's what it looks like when the carbon shares its 4 electrons with 4 different hydrogen. Could share it with something else, but we're going to name it carbon tetra for the 4 hydride, IDE ending. Notice we don't say it monocarbon tetrahydride. Okay, that's actually methane. We do maybe have a common name for it, especially organic chemists with all their carbon-containing compounds. Okay, so for example, glucose is the easy name for C6H12O6, right? We use it a lot in chemistry. However, the proper scientific name would mean putting an hexa in front because that first carbon is 6. So hexacarbon, there's 12 hydrogen. This is a rare situation, yes. Duodecahydrogen, and then hexaoxide, right? IDE ending. Yep, it's a little fancier than glucose, but that's okay. At least we're accurate. Now, one exception, if hydrogen is listed first, it's actually a cation. It's not going to share. Yeah, hydrogen could go both. It could be an ion or it could be covalent. So that's one of the few exceptions. And then it actually becomes an acid if it's a hydrogen listed first, like hydrogen or hydrobromic acid is what we're going to say, hydrofluoric acid, nitric acid, sulfuric acid. We do not get into that in this class much yet until we talk about acids. So don't worry, but you might want to know if hydrogen's listed first, it's a cation, okay? And of course, when you're listing these compounds, you wouldn't actually put the charges down because they are neutral compounds like that. All right, but you got to make sure the charges match if it's ionic. Yeah, so covalent, that's how that works out. And that's all that we're going to do on the review for this. So your assignments, you may just have to determine whether it's a covalent compound or an ionic compound. Just look at the first letter and see if it's a cation. Basically, if it's a metal, it's ionic, it's a cation. And if it's not, it's non-metal, it's going to be a covalent. All right, thanks for coming along on this review. I hope you have a good time with it with your assignment. Let me know if you have any questions or problems. Have a good day.